Good morning. Myself, Engineer Srishti Chaudhary, working as lecturer in Electronics and Communication Engineering branch in GPGC Patiala, that Government Polytechnic College for Girls, Patiala. Today I am here to discuss on the topic of the receivers. In our daily routine life, we have come across this word very oftenly, receivers and transmitters. And in the communication system, we have discussed that the transmitter and the receiver are linked through a communication medium, and that communication medium can be wireless or that can be a wireline medium. Now, what basically a transmitter and what basically a receiver is? Transmitter, in a simple statement, we say transmit the signal to a particular destination, and receiver receives that signal at a particular destination. But what exactly a receiver is and what types of receivers are we using in various applications, this lectures deal upon the various types of receivers. Now, coming upon the basic statement of receiver, receiver is an electronic equipment which picks up the desired signal and rejects the unwanted signal. That is, it selects your desired signal and rejects undesired or unwanted signals that are present in the atmosphere. After the signal has been desired, it demodulates the carrier signal to get back to the original modulating signal. In the diagram shown before, we are having an example of a real-time application in daily routine. You are having a receiver, radio receivers commonly used, everyone uses the receivers to select a particular signal. That is, we tune the receiver to a particular signal, rejecting all other signals. That tuning means that you are selecting to a particular frequency to get the signal of that particular frequency, and we are rejecting all other signals. So, what is the basic function of your radio receiver? First, it intercepts the incoming modulated signal, that is, it detects your signal that has to be at the receiving end. After it has been detected, it selects the desired signal and reject unwanted signal. That is, what is the desired, what signal do you want, that particular signal has been selected and other unwanted signals are rejected by your receiver. After it has been received, the signal has been selected by the receiver, it amplifies the selected RF signal. Because the signals can be weak, the amplification process is done at the receiver point. After it has been amplified, it detects the modulated signal to get back original modulated signal. That is, detect means at this point we are doing the demodulation process to get into the original form. After we have provided the demodulation to the signal, it is again amplified to have a modulating frequency signal. So, what is the basic design criteria of your receiver? We have discussed what a receiver is, what a particular function of the receiver is. Now, what are the characteristics or parameters that has to be kept in mind when you have to design a receiver? The radio receiver has to be cost effective, and the requirements are as follows. It has to work according to the application. As for what particular application you have designed a particular receiver, you have designed it to work as a radar receiver or as a broadcast receiver or as a television receiver or AM or FM signal receivers. According to that particular requirement of the application, your receiver should work, and it should tune to and amplify that desired radio station that is needed and filter out all other stations, that is, it should reject all other unwanted stations. Demodulator has to work with all radio stations, that is, regardless of your carrier frequencies. This is the basic design criteria of your receiver. Now, receivers can be classified according to the application and according to the fundamental aspect. According to the application, it means at what particular application you are using a radio receiver, as AM, FM, radar receivers, broadcast receivers, communication receivers. Now, coming to the AM receiver, the AM receiver receives the broadcast of speech or music from AM transmitters which operate on long wave, medium wave or short wave bands. It is the frequency bands at which your AM receivers operate. FM receivers receive broadcast programs from FM transmitters and operate on very high frequency or ultra high frequency bands. Next is the communication receivers. Communication receivers are used for reception of telegraph and short wave telephone signals. That is, communication receivers are used other than your broadcast purposes. Television receivers used to receive television broadcast in very high frequency and ultra high frequency bands. Radar receivers are used to receive radio detection and ranging signals. These are mainly used in military purposes. Now, depending upon the fundamental aspects, we are having two types of receivers. One is your tuned radio frequency receiver and second is your super heterodyne receivers. These receivers will be discussing in detail in the lecture. Now, these three, the basic criteria of the receivers we are going to discuss, that is tuned radio frequency, super heterodyne receiver and the communication receiver. Tuned radio frequencies in short composed of RF amplifiers and detectors, and there is no frequency conversion in case of your TRF, and it is not often used due to the drawbacks involved in it, and it is difficult to design its RF stages and obtain a high gain. In super heterodyne, the modification from TRF is done so that the drawbacks can be overcome. We down convert the RF signal to lower IF frequency and amplification takes place at intermediate frequency stage. At the communication receiver, you down convert the RF signal into two intermediate frequencies. One is higher intermediate frequency and next is the lower intermediate frequency. Now coming to the detail of your tuned radio frequency receiver. As the name indicates, what is your tuned radio frequency receiver? It tunes to a particular frequency, that is you select one particular frequency and you reject all other frequencies or all other signals that are coming into the antenna at the receiving end. This is the basic block diagram of your TRF. At first block shows your tuned radio frequency amplifier at which you selects a particular frequency and it is amplified and given further to the detector stage. At the detector stage, you are having the various detectors to have the demodulation process to be done so that you can get the original signal back in the form. At last you get the original signal, it is further given to your AF amplifier, that is your audio frequency amplifier, and at last you are having the amplified modulating signal. So your TRF receiver includes an RF stage, a detector stage and an audio stage. RF stage have the process of your select, that it selects a particular frequency. Detector stage have the principle of your demodulation, that it provides a demodulation process to the signal so that it can be into the original form. And audio stage provides the amplification to your detected signal, that is your demodulated signal. 2 or 3 RF amplifiers are required to filter and amplify the received signal to a level sufficient to drive the detector stage. Why 2 or 3 RF amplifiers are needed? We have done it in the your EDC subject related to the topic of multi-stage amplifiers, that multi-stages are needed so that you get a required level of power or amplification with respect to your signal. Now this is the detailed diagram of your tuned radio receiver. Here you are having a receiving antenna. At the receiving end, you are getting the signals. At the receiving antenna, there are various signals present in the atmosphere in the form of EM waves, but only a particular signal that is desired by you is detected by the antenna coupling network. After you are having more than one RF amplifier stages, here it is shown 3 RF amplifier stages, and then a gang tuning is provided between these 3 RF amplifier stages. We will discuss that what is this gang tuning. In short, it is a simultaneous tuning between the various amplifiers or various components of the device, so that change in a particular component of the circuit will affect the change in the another component simultaneously. After the RF amplifier, you have selected the particular frequency, you have amplified that particular frequency, it is given to the audio detector. This is the detector stage. As we have discussed, this detector stage demodulates your signal. This detector stage, according to your application, can be any detector, as you are dealing with AM or FM or other particular receivers. As per AM and FM, you are having the various detectors. As you are having balanced modulator, you are having slope detector. There are various detectors. At last, it is given to the audio amplifier stage. At the audio amplifier stage, you provides the amplification to the original modulating signal that you get after the demodulation, and at last it is given to the load, and here the load is shown in the form of the speaker. Here the waveforms are shown, that at the RF stage you are having RF signal, and at the audio amplifier you are having the original signal in the form of this. So what is various sections performing? We are having a brief introduction. RF section is the receiver front end, and it is used to detect the signal. After the signal has been detected, it band limit the received RF signal and amplify the received RF signal that you have received. The detector demodulates the AM wave and converts it to the original information signal. After that, it is given to the audio section that is used to amplify. Now, what are the various advantages of your tuned radio frequency receiver? It is simple to design and it allows the broadcast frequency of 535 kHz to 1640 kHz, and it has the high sensitivity. That is, the weak signals can be sensed very easily by your tuned radio frequency receivers. Now, the disadvantages of TRF. At higher frequencies, it produces difficulty in design and it has poor audio quality. The main drawbacks related to your tuned radio frequency receiver is instability, variation in bandwidth, and poor selectivity. Considering these three drawbacks in detail, what they have the effect on your TRF, first is the instability. Now, due to high frequency, we are dealing with the radio frequencies that are high frequencies. Due to high frequency, multi-stage amplifiers are susceptible to breaking into the oscillations. Now, we have done the concept of the feedback in your EDC subject, that feedback is provided in the circuit, and if it is a positive feedback, it works as an amplifier, and if it is a negative if it is a positive feedback, it works as an oscillator, and if it is a negative feedback, it works as an amplifier. That is, if the feedback is in phase or it is out of phase, it depends the working of the component, that it will work as an oscillator or as an amplifier. In case of your TRF, as gain of RF amplifier is very high, a small feedback from output to input with correct phase can lead to oscillations. Here the correct phase means the positive feedback. That is, you are having the feedback. If that feedback results in the positive, that is in phase to your input, that will give the oscillations, and it takes place due to stray capacitances. Why due to stray capacitances? Because it's as reactance of stray capacitances decreases at higher frequencies. We know it is inversely proportional. As your frequency increases, your reactance decreases, resulting in increased feedback. This increased feedback forces the device to work as an oscillator instead of an amplifier, as now you are having the feedback in positive, that is in phase. If your feedback start to develop in phase, that is, you are having a positive feedback, it will force your device to stop working as an amplifier and it will start working as an oscillator. That is not desired. That is, the stability of the device is removed. Now, second is the variation in bandwidth. Now, what is the variation in bandwidth? The bandwidth is inconsistent and varies with center frequencies. As your center frequencies vary, your bandwidth varies when tuned over a wide range of input frequencies. Now, if the frequency increases, your bandwidth increases. Thus, the selectivity of the input filter changes over any appreciable range of input frequencies. Now, this can be explained with an example. Suppose we required a bandwidth of 10 kHz, and we know that your TRF has the frequency range of 545 to 1640 kHz. So, you have the lower frequency 545 kHz and the higher frequency as 1640 kHz. So, quality factor with respect to these two frequencies, quality factor 1 and quality factor 2, we know quality factor is equal to frequency by bandwidth. Corresponding to these two frequencies, you have quality factor 1 as f1 divided by bandwidth, that is 54.5, and quality factor 2 as f2 divided by bandwidth is 164. But practically this quality factor is limited up to 120, that is, it cannot exceed up to the limit more than your 120. So, 164 is not feasible practically if we go for the applications. So, considering the Q limit 120, your bandwidth changes. As bandwidth is now coming to the vice versa equation, your bandwidth is equal to f2 by q2. Considering these parameters, substituting these parameters as f2 1640 and q2 120, your bandwidth changes to 13.6 kHz. Now, we required bandwidth of 10 kHz, but due to the practical limit of quality factor, now we are having the bandwidth of 13.6 kHz. That is, adjacent channels is picked up, resulting in variation in bandwidth. Your bandwidth varies. As what required bandwidth we are not getting it, but we are getting the another bandwidth which was not required by us due to the limit of your quality factor, that is 120. So, third is the poor selectivity. The gains are not uniform over wide range of frequency, and due to higher frequency, ability to select desired frequency signal is affected. This can be again explained as per the variation in bandwidth. You are having the variation in bandwidth due to which you are picking up the adjacent channel. Now, that adjacent channel is picked up. That means you are not selecting the desired signal, you are selecting a undesired signal that is tuned to another bandwidth. You are not having a signal at 10 kilohertz bandwidth, you are getting a signal at 13.6 kilohertz bandwidth. So you are not selecting the desired signal, you are selecting the undesired signal, so you are having a poor selectivity. So due to these drawbacks, your tuned radio frequency receiver are really used, and these drawbacks are overcome in your superheterodyne receiver, that is next receiver, superheterodyne receiver. The shortcomings of TRF receivers are overcome as superheterodyne receiver. How these are overcome? We are proposing a concept of intermediate frequency in case of your superheterodyne receiver. This intermediate frequency is a kind of lower frequency, that here you are converting a higher frequency signal to a lower frequency signal, so that the drawbacks that were related to your higher frequencies are overcome in case of your superheterodyne receiver. This is the basic block diagram of your superheterodyne receiver. Again, you are having a RF amplifier, IF amplifier, detector and AF amplifier. What changes occur in superheterodyne receiver is this: you are having a mixer and a local oscillator. That was not in case of your TRF, that is tuned radio frequency receiver. This mixer and local oscillator is needed so that you can get an intermediate frequency, that is your IF, that is lower frequency with respect to your radio frequencies. A mixer performs a basic principle, mixes the two frequencies to get a new frequency. That is two frequency, we are having a signal frequency and a local oscillator frequency. Mixer processes these two frequencies to get a new frequency, that is your intermediate frequency. It works on the principle of heterodyning. What is mainly a heterodyning? As the name of the receiver is superheterodyne receiver, the name is due to the principle involved, that is heterodyning. It is the mixing of two frequencies together in a nonlinear device, or to transmit one frequency to another using nonlinear mixing. So it is also known as frequency conversion, as you are converting a higher frequency signal, that your RF signal, to a lower frequency signal. High frequency down converted to a low frequency, and that low frequency is named as your intermediate frequency. So a superheterodyne receiver converts all incoming radio frequency signals to a lower frequency, that is known as your intermediate frequency. Now, how the drawbacks are overcome in case of your superheterodyne receiver? Considering the first drawback that was made in case of your TRF, that was stability. As your high frequency is down converted to intermediate frequency, that is the lower frequency, so the reactance of stray capacitances will not decrease as it was at the higher frequencies, so resulting in increased feedback. Your stray capacitances were decreasing in case of your TRF, that results in increased feedback, and that increased feedback resulted in to correct phase, that is in positive feedback resulted into the breaking into the oscillations. But in this case you are not having a high frequency, so you will not having the reactance of stray capacitances to be decreased, so you will not having the increased feedback, and in turn you are not having a positive feedback that will result into the oscillations. Second, there is no variation in bandwidth, as intermediate frequency ranges 438 to 465 kilohertz in case of AM receivers, and it is mostly value of considered IF is 455 kilohertz. So that will be appropriate for your Q limit, that is 120. And the better selectivity is there, as no adjacent channels are picked due to the variation in bandwidth. As there is no variation in bandwidth, you are having a lower frequency range, that is the intermediate frequency, which will not affect your bandwidth limit, and it will not affect your quality factor limit. So your not adjacent channels will not be picked up, so there will be the better selectivity in case of your superheterodyne receiver. So all these three drawbacks that occurred in case of your tuned radio frequency are overcome in case of your superheterodyne receiver. Now this is the detailed block diagram of your superheterodyne receiver. You are having a pre-selector and RF amplifiers. The output of your RF amplifier, after it has the signal has been selected and amplified, it is given to the mixer. At the mixer, the second input is of the local oscillator frequency. After these two frequencies are mixed, the output is given to the band pass filter. Mixer at the mixer, you are having the harmonics produced resulting or corresponding to these two frequency signals, that is your signal frequency Fs and local oscillator frequencies F0. So the harmonics produced will be F0 Fs, F0 plus Fs and F0 minus Fs. but at the mixer only the difference component is allowed to go or pass further, rejecting all other 3 harmonic components. That is, only F0 minus Fs is allowed to pass further. By the mixer band pass filter will allow only the difference component. After it is allowed, you are having now the intermediate frequency. F0 minus Fs is your intermediate frequency. That is, now you have down converted the higher frequency radio frequency into the lower frequency signal. Now this is further given to IF amplifier. You are having now IF frequency signal. This IF frequency signal is given to the IF amplifiers to amplify the signal. Further it is given to the audio detector. Audio detector will provide you the demodulation to get in the original signal, and further you get the original signal. It is again amplified by the audio amplifier in the original form, and it is then given to the load circuit, and in this case also we have shown a load circuit as a speaker. So considering the RF section consists of a pre-selector and an amplifier as shown in the diagram. The pre-selector is a broad tuned bandpass filter with an adjustable center frequency. Your center frequencies can be adjusted by the pre-selector, that is used to reject unwanted radio frequency and to reduce the noise bandwidth. The adjustments is done at the pre-selector so that you can reject the unwanted radio frequencies and you can reduce the noise bandwidth. The RF amplifier determines the sensitivity of the receiver and a predominant factor in determining the noise figure. Mixer and converter section, as I have discussed, it consists of radio frequency oscillator and a mixer. Second input is from a local oscillator, and the choice of oscillator depends on the stability and accuracy. As we have discussed, there are number of oscillators, as you are having Colpit oscillator, Hartley oscillator, and if you need the better stability, you have the crystal oscillator. Mixer is a nonlinear device that convert radio frequency to intermediate frequency, that is heterodyning process we have discussed. The shape of the envelope, now this point has to be understood very clearly, that the shape of the envelope, the bandwidth and the original information contained in the envelope doesn't change, it remains unchanged. Although the carrier and the sideband frequencies are translated from radio frequency to intermediate frequencies, you are only transferring the carrier and sideband frequencies to RF to IF, but the envelope and the bandwidth and the information that was contained in the envelope, it is not changing, they are unchanged, only the carrier and the sideband frequencies are translated. Now after you are having the intermediate frequency, you have done the heterodyning processing, that is frequency conversion has been done. It is, you are having the intermediate frequency that is given to the intermediate frequency section that contains of your IF amplifiers and bandpass filters to achieve most of receiver gain and selectivity. The IF is always lower than your RF because it is easier and less expensive to construct high gain stable amplifiers for low frequency signals, and IF amplifiers are also less likely to oscillate than their RF counterparts, as we have discussed, because your intermediate frequency amplifiers are at lower frequency range as compared to your radio frequency range, so the oscillation problem was overcome in case of your superheterodyne receivers. Now coming to the detector section, detector sections we have discussed, it converts the intermediate frequency signals back to the original source information by the process of demodulation. That demodulates the signal, and it can be as simple as signal diode. In the case of construction, that your detector section can be as simple as just having a single diode, or it can be as complex as your PLL, that your phase locked loop circuit, or a balanced demodulator. It again depends upon the application you are using, what particular requirement you are having. Now, at last you are having a audio amplifier section. It comprises of several cascaded audio amplifiers and one or more speakers, and this audio amplifier section amplifies your signal that you have get after the demodulation. Now AGC, what is automatic gain control? This automatic gain control is a type of feedback from output back to the input. It controls your gain, the gain of the device. Now why the gain of the device has to be controlled? In simple sense, you are having various signals coming at the receiving end, but the various signals that are coming at the receiving end has not to be of same strength. Some signals can be of weak strength, some can be of strong. So your weak signals are adjusted with the higher gain and your strong signals are adjusted with lower gain. So automatic gain control provide a constant gain for that weak signals and that strong signals, so that you get a constant signal. So it adjusts the IF amplifier gain according to signal level. AGC is system by means of which overall gain of radio receiver is varied, and it is automatically with the variations in strength of received signals to maintain the output constant. As I have discussed that your received signals varies, it cannot be of constant amplitude or magnitude. Some can be weak signals, some can be strong signals. So at the output you need to maintain a constant. For that your automatic gain control is provided. Automatic gain control provides adjustment or compensation for the weak and strong signals so that they can have a constant output. AGC circuit is used to adjust and stabilize the frequency of local oscillator, and the types of AGC are no AGC, simple AGC and delayed AGC. This AGC topic will be discussed in detail in your next EduSet lecture, receivers 2. Now we have done the frequency conversion is the principle of your superheterodyne receiver, that is heterodyning is done. Now what merely a frequency conversion is there in the superheterodyne receiver and what it was there in the modulator that you have done. Frequency conversion in the mixer stage is identical to frequency conversion in the modulator, except that in the receiver the frequencies are down converted rather than up converted. In these receivers you down convert the frequency, that you are converting the frequency, but frequency is down converted from a higher frequency to a lower frequency, but in case of your modulators it was up converted. In the mixture, RF signals are combined with the local oscillator frequency. Local oscillator is designed such that the frequency of oscillation is always above, your F0 is always greater than your Fs. So the desired RF carrier by an desired RF carrier by an amount equal to the intermediate frequency, that is your center frequency. Therefore, the difference of RF and oscillator frequency is always equal to your intermediate frequency, that is your F0 minus Fs is equal to IF, that is your intermediate frequency. So the adjustment for center frequency of pre-selector and local oscillator frequencies are gang tuned. I have discussed this gang tune. It is a simultaneous connection between the components, that is the two adjustments are tied together so that a single adjustment will change the center frequency of pre-selector and at the same time change the local oscillator. That is, you are having a simultaneously connection between the local oscillator and the pre-selector. As the frequency of one particular component changes, at the same time the frequency of another component changes. That is the gang tuning required, or why the gang tuning is installed here. When the local oscillator frequency is tuned above the radio frequency, it is known as your high side injection, and when the local oscillator frequency is tuned below the radio frequency, it is known as your low side injection. Mathematically, it can be expressed as high side injection as FRF plus FIF, that is radio frequency plus intermediate frequency, and at low side injection it is FRF minus FIF. Here it shows the basic block diagram of your intermediate frequency superheterodyning procedure. You are having a pre-selector here. Pre-selector selects a particular signal RF amplifier. You are having this mixer or converter connected to the local oscillator. Here local oscillator and pre-selector are having a gang tuning, that is a change here at the pre-selector of for a particular frequency will have a change in local oscillator also at that same time. You are having the center frequency as 900, 905 and 895. Error of 5 kilohertz is considered here with the difference of 5. So regarding this, you are having a frequency spectrum for your RF input. This is shown on frequency spectrum. This signal is provided further to RF amplifier. RF amplifier selects the signal, amplifies the signal, and that is given to the mixer or converter. Second input to the mixer or converter is from local oscillator frequency. Here we have assumed the local oscillator frequencies as 1355 kilohertz. Now after considering these two, only the the difference component be allowed by the mixer converter, that is F0 minus Fs. So we are having three combinations of F0 minus Fs, that is 1355 minus 900, 1355 minus 905, 1355 minus 895. So you are having these three different frequencies, 450 kilohertz, 455 kilohertz and 460 kilohertz. Mainly uses this value of intermediate frequency, that is your 455 kilohertz. That is given to the band pass filter and next to the intermediate frequency amplifiers. So this is the frequency spectrum of your intermediate frequency signals. Now we have done the TRF, that is tuned radio frequency receiver, and superheterodyne receiver. So just coming to a simple comparison between these two receivers. At your TRF you are not having any type of frequency conversion, but at superheterodyne receiver you are having a frequency conversion. At TRF there is no intermediate frequency, as you have not converted any frequency, you are not having a heterodyning principle. In case of your TRF there is no intermediate frequency, but in case of your